Good morning, good day, and good evening to all of you around the globe. Welcome to this webinar regarding measuring gas flow in power and energy, and with a focus on increasing safety and reducing cost. So you hear right now the voice of Oliver Seifert. I'm from Endress Hauser Flow. I'm the head of strategic product management for Votex and thermal mass flow meters. And you will hear my voice through most of the presentation. And with me, I have two specialists. First, we have Uwe Wagner. Uwe, maybe you have a few words about yourself.
Yes, good day to everybody around the globe. My name is Uwe Wagner. I'm at Endress Hauser Group Services, responsible in Endress Hauser as a global industry manager for power and energy, located in Switzerland, in Rheinach, and happy to host with you today this seminar, and looking forward to this fantastic news we want to share with you.
Perfect. And in the background, we have Ahmed Khater. He's from Endress Hauser Temperature and System Components. So in Bavaria, that's our division for temperature mainly and the system components. And he's an application engineer for temperature engineered solutions with a strong background in power and energy. So especially when it comes to gas-fired power plants. Content of today is we're going to check out the power and energy gas applications. We will discuss some industry observations. I will show some flow technologies for gas. We'll discuss corrected volume. Then we will discuss the respective applications like natural gas, combustion air, hydrogen, and then we'll come to some recommendations. So here you see the main instrumentation in a combined power plant, combined cycle power plant. So we see that you have a lot of instrumentation like flow, level, pressure and temperature all around over the place. So for instance, here at the Hursk, at the steam drums, you have some important level measurements. You've got a lot of analytical measurements because the quality of the water and the steam is of high importance. It's important quality that Endress Hauser knows to measure. Then you have the raw water for cooling that you make cooling water of. So and over the place you find a lot of measurements. But what we focus on today, that's the gas side, and we will focus on natural gas. We'll focus on combustion air, and we will focus on hydrogen for generator cooling. So here you see those in detail. So the inlet for natural gas, but you also have the measurements down to the power blocks. So at this metering station, then here we see the air measurement for the combustion air, and here we see the generator cooling for the hydrogen cooling. So what are typical industry observations that we see? First, how can I optimize the combustion in my combined cycle power plant? And how can I check the efficiency of my improvements? The authorities require the use of hazardous area and cell instrumentation. Where do I find the relevant information for the devices used? And how can I be sure the flow measurements are still okay, which is an important question, especially when it comes to measurements of stuff that has an influence on the environment. So which gas flow measuring technologies are there? So first, DP flow is very traditional. You find that a lot in these power plants. The benefit is you have a relatively low operation expenditure, so purchase cost is relatively low for large diameters. However, these guys tend to drift, and you have a limited turn down as well. Then you have Votex meters. They're volumetric, but usually they're limited in line size up to DN300 12-inch, and they lose the signal at the low flow. So it is an important technology for steam, but also for water and gas. Then here we have thermal mass flow meters. They come with a low pressure drop, have a large turn down, but they struggle with wet gas. And they are the first choice for standard natural gas, I would say, for industrial gases and for compressed air. Then Coriolis meters, they come with the best accuracy and they don't require any inlet runs. That's a big benefit of this technology. And however, they have a high pressure drop. So this is why in some gas applications you won't use them. But here in power plants, we find these applications. Primarily, you find them in custody transfer applications. So if you require prime accuracy. Then ultrasonics, they come with a low pressure drop, have a large turn down, and they can handle wet gas. But they struggle with low attenuation gases like hydrogen or carbon dioxide. And here we have some specialists for wet biogas and for wet natural gas. Corrected volume. So typically, if you measure gas in a combined cycle power plant, you will want to measure that gas in normal meters cubed or standard meters cubed or standard cubic feet. And this corrected volume is actually a mass term. So you see, you take the actual volume measurement, and then you have to compensate that. You have to multiply that with the relation between operating pressure to reference pressure. Reference pressure is typically 1013.25 millibar or 14.696 psi times the relation of temperature at reference conditions. For normal meter cubed, that's 0 degrees C, so 273 kelvins. Here it's important that you're using kelvins if you do the calculations yourself. Otherwise you have a wrong term. So this is highly important. And then they measure temperature again in kelvins. So flow computers and so on, they will do the conversion themselves. And here you have the relation of the compressibility factors. So at reference conditions to operating conditions. So reference temperature, by the way, for standard is 15 degrees C or standard cubic feet, it's 60 Fahrenheit. The beauty is if you're now using a mass flow meter, the world becomes much easier because that corrected volume is now mass divided by the reference density. So this reference density, you either know, okay, it's a gas that doesn't change its composition, so you just divide the mass by the reference density, or you read that in from a gas chromatograph at the inlet of your combined cycle power plant. So here we already see that natural gas application at the metering station. So at the inlet, that's usually a custody transfer application. So in Europe, MI002 requirements. And you want to have prime accuracy because here you're talking about a lot of money. You're talking about literally millions per year that you're burning in natural gas. And typically you have a gas chromatograph because you want to know what do I get supplied. So you know the quality of what is coming in. So what you want to measure as well is to check the flow of flow to the different power plant blocks. What you also find is LNG. So on the left-hand side, you see the inlet of a combined cycle power plant here in Europe. And on the right-hand side, you see an LNG application, so where this natural gas is liquefied. So that's at 162 degrees C minus, where you find liquid natural gas. So that's good for storage, for instance, of the natural gas. But then you will actually convert that to a gas before you burn it. So here's an example where we replaced a traditional meter. That's a turbine meter, turbine flow meter, that's the TFM. And when this customer installed the ProMass, he found a drift between the turbine and the ProMass. So first he thought the mass flow meter of ours was wrong, but he found out later, because both meters were sent for calibration at Pixar on natural gas. So that's a custody transfer authority in Europe. And they found out that the turbine had an offset of 0.7%. So this customer told us that this accuracy improvement for him meant savings of 1 to 2 million euros of natural gas per annum. So very interesting reference here from Europe in the Munich area. Here's another reference. So that's a bigger line size. So here you have two of our largest Coriolis meters. So two of 14-inch meters in parallel, measuring this inlet to a combined cycle power plant in Nigeria. So the first choice when it comes to natural gas in a combined cycle power plant at the custody transfer measuring station, from my perspective, that's a mass flow meter like our ProMass F or X. So you get the best accuracy there is on the market. You don't need compensation requirements. So you directly get the mass and you divide by the reference density of your gas chromatograph. It's a no-brainer that even though you may have a custody transfer ultrasonic, that has on paper a relatively good accuracy, but then you have to add the uncertainty of the component's pressure, temperature, and also the gas composition, and all of a sudden you have much higher uncertainties than what you get with such a solution. So this is also suitable for cryogenics, these mass flow meters, and they come with SIL 2, so for IEC 615 or 11 applications. Or here on the right-hand side for submetering to the different power blocks. There you may want to use such a prosonic flow. That's an ultrasonic meter for check metering also. So checking such a custody transfer meter, if that's still okay, or for submetering to the different power blocks. And you have short inlet runs, but it's also multivariable. So it's got integrated pressure and temperature compensation, as you can see here. We come to the next application, that's generator cooling. So hydrogen cooling, so this is what we see here. So hydrogen is a low density gas. Just one second, I just activate here. We have the hydrogen cooling to the generator. It's a low density gas. It got low attenuation also. That's why usually you don't use ultrasonics here. And it's at low pressures also, so 7-8 bar-ish. We as Endress Hauser, we've got a lot of experience here in this application using DP, Votex. We've been using Coriolis thermal mass. I do like the Coriolis here at this application because of its gasket-free construction, and it's got an optimum accuracy, and you find a loop-powered option as well. The thermal mass is, however, used quite a bit. So we've got hundreds of references in the US, especially. So here you have no pressure drop. It measures even the smallest flow rates, hundreds of references really in gas turbine cooling, so with GE. So when it comes to thermal mass, hydrogen is, however, I must say, quite a challenging gas because of the measuring technology itself. The thermal mass, it provides you directly the mass of or the corrected volume of your hydrogen. It's multivariable, you don't have pressure drop, and you've got a large turn down, and you can also measure at these ranges. However, you see here, this is where we calibrate our meters on air, and this is where you use the meter in hydrogen. So the characteristics are quite a little different. That's why, so in the US, very often these meters are actually recalibrated on hydrogen. That's done by the OEMs we have there. And so that's one challenge solved. So you can improve the accuracy. This is what you see here. So that's a calibration on hydrogen. The challenges till now were that you need a lot of inlet runs with thermal mass. So here we will have a solution with our next generation. They measure flow in only one direction. So in a hydrogen generator cooling solution, you would like to know, is it sometimes the hydrogen coming back? So here, this is something we can do in the future. You get wrong measurements in case of moisture or dirt. This is also solved in the future with our heartbeat technology. And the existing technologies, they all tend to drift, but there we have a solution as well. So the special calibration, however, this will be a requirement still in the future. However, I must say, if you don't calibrate, the repeatability is still good with these meters. So what are the solutions for hydrogen? First, we have TMAS 300-500. He's, as I mentioned, the first choice. This is this future device. It's coming later this year. So only a few weeks or months we are away to get the release. The beauty is you don't get any pressure drop with these guys. You have an integrated flow conditioner option here with short inlets. So this flange meter comes with a flow conditioner welded in. And when it comes to a bidirectional solution, you have the flow conditioner at both sides even. So to get short inlet runs. So we can even shorten the inlet runs to 2dn and with an increased uncertainty, however. This is not a problem. These meters are drift-free, the sensors, the new sensors that we've got, and they can detect moisture and drift using heartbeat technology. And we come also with a status input for purging. So if you use switching between the hydrogen and air for air purging, so you can measure both actually using this meter. So this is beautiful for this technology here. And it comes with SIL2. This is, however, still pending this approval. That takes some months, maybe. Coriolis, so here the ProMass A200, that's a 2-wire mass flow meter for small line sizes, as you usually use here in hydrogen. That's the best accuracy you can get. It's loop powered, and it's got nice diagnostic capabilities as well. And it's coming with SIL2 and even Zone 0 approval for the device. Here inside the tube, okay, both have got that. Zone 0 inside the tube and Zone 1 for the electronics. When it comes to combustion air, so this you do measure to adjust the air to fuel ratio. Typically here you have a lack of inlet runs. You find rectangular ducts or round tubes here, and typically you're using insertion devices like Pitot tubes or thermal mass flow meters. So if you compare the technologies that are most common here we have an application to, this is a fire tube boiler, okay, that's a small one, but also here you see a rectangular duct of combustion air being used, and here you see this thermal mass flow meter, and there you could see also maybe in other applications a Pitot tube. So the mass flow meter, that has the benefit, you get the mass output directly, you've got a great turn down, but moisture can cause a misreading, that's an issue, and you have a certain inlet run requirement. Of course, with the insertion, you can't install just here a flow conditioner very easily. With DP flow, the primary measurement is DP only, so you need compensation by pressure and temperature. And they're subject to drift, and their turn down is really low. Typically, you find only a turn down of 3 to 10 to 1 as opposed to 100 to 1 using thermal mass. And the averaging effect, however, reduces the inlet runs required. So those are our solutions when it comes to combustion air measurements, as I mentioned. So mainly the TMAS 300-500, typically as an insertion device you will find here. It doesn't have any pressure drop. You have got integrated flow conditioner options for the flanged version only. So this is rather for smaller line sizes, but this is maybe relevant for other applications. It's drift-free. You can detect moisture. That's also a beauty. So that's one solution for the former problems of the thermal mass flow meters. And only wait a few weeks or months, and this one is available. Pitot tube with the delta bar S, that's loop powered. You've got an averaging effect, and it's compensated, for instance, in a RMC 621 flow computer by pressure and temperature. Also, this comes with SIL2, however, not for mass, for the DP only. So if you need SIL2, then you need SIL2 also for pressure and for the temperature. So next one. Sorry, here we see a heartbeat. So I've been talking about this heartbeat technology. This is integrated in our devices, and both the thermal and the Coriolis meter, they come with heartbeat diagnostics. That means they have error messages in line with the NAMOR recommendation NE 107. So there you see, is maintenance required? Is the device okay? Or is it out of spec? or is it broken? Then you can do verification. So this is important if you want to prove to the authorities, yeah, we believe this measurement is still okay. And this is typically if you have measurements that have an influence onto the environment, like natural gas measurements. And last not least, monitoring, that can help you to detect, to do some predictive maintenance to get some information out of these devices. So heartbeat also, as I mentioned before, for the thermal mass, for instance, enables you to detect if there's moisture present, or if the device is drifting because of coating on these sensor probes. So we come back to the industry observations. So first one was, how can I optimize the combustion in my combined cycle power plant? So the optimum accuracy is always the foundation. So if you want to know how efficient you really are, then you need good measurements, of course. And the best accuracy you can get using the ProMass for the natural gas measurement. Then we said the authorities require the use of hazardous area and sill instrumentation. Where do I find the relevant information for devices used? So especially for the functional safety parameters, this is very easy. So these parameters can be found under endress.com/sill. So all devices that have IEC 61508 or are suitable for SIL 2, SIL 3, they have got this FMEDR, the documentation of the safety relevant parameters. And for hazardous area devices, of course, we have all the entity parameters documented. Then how can I be sure the measurements are still okay? I just mentioned you can use this heartbeat technology, especially the verification. Creating verification reports can help you to make sure that you can still trust the measurement and prove that to the authorities. Last not least, I'd like to share with you some references, so some YouTube videos explaining the flow principles. So if you go to the Endress Hauser YouTube channel and you find easily these video channels, and each one is, you see, it's between 4 or 5 minutes, typically, these videos, and they explain very nicely how these flow principles are working. And another one, here you have our complete offering for the combined cycle power plants. It's a very nice brochure that Uwe Wagner did some time ago. I really like it. So here you have the QR code to go into that. So with that, Uwe, do we have any questions?
Yes, for sure, Oliver. Thanks for the presentation first. We have 2 questions coming in here, and I want to encourage the audience to use that functionality and place your questions in case you like to have a discussion on that. The first one is, from a point of view of economics, which is the better thermal mass flow? Which is the better, a thermal mass flow or a mass flow meter for hydrogen cooling application? So I guess this is the question, is it better from an economical point, thermal mass flow or Coriolis mass flow?
From a pure OPEX perspective, it's clearly the thermal mass. That is cheaper. However, if you add now the hydrogen calibration, this is also, again, this is more expensive than the device itself, I would say. Now it depends on how many devices you have, but that's an important cost driver. But typically, the Coriolis meters are about, I would say, double the price of a thermal mass flow meter.
Good, thank you, Oliver. And the next one is related to slide number 19 for chimney emission gas monitoring. What should you recommend among TMAS 305, 500, insert type, or Pitot tube?
For chimneys,
chimney emission gas.
Yeah. So there, I must say, I don't see many applications of neither. I at least haven't seen them that much. But the problem with the TMAS is, okay, you wouldn't have any issues with the with dirt sitting on it because the combustion is relatively clean. However, because you have a relatively large duct, then it's hard to find a good point. And temperature limitation is now 180 degrees C. I'm not sure if that's sufficient. Typically, I think you should be lower if you have enough energy taken out through the Hursk. The other one, Pitot tube, from an pure economic standpoint, the Pitot tube is cheaper.
Okay. So I have also seen some of these application and chimneys with Pitot tubes, and due to, you mentioned that already, due to let's say particles that can block the tube holes, Pitot tube holes, they have added special purge systems, air purge systems,
air purging,
to purge that. Yeah, to purge that Pitot tubes. This ones I have seen in the industries, depending on the, as you also said, onto the duct or onto the chimney size. Good. There is another question from Ali. Which flow meter is suitable for flare gas?
Flare gas, you find some Venturi types, you find some Pitot tubes, but there are ultrasonic meters. They are currently, I think, the best technology, but there are none from Endress Hauser, I must say.
Good.
So my personal preference for flare typically would be these. However, it depends on the flare now. So we have a lot of flares in refineries, refinery flaring. That's, the problem is that you have various things going through there. So thermal mass won't work because the gas composition keeps changing. However, we have a lot of applications of thermal mass flares in Russia, in Siberia, where you flare the associated petroleum gas, and the composition of that is relatively stable. And that's actually, at the end of the day, it's natural gas.
Good, very nice. Then we don't have any further questions in the chat so far. 1 second, there's just coming one in. Oliver, what is the velocity limits for Coriolis and gas applications?
So what will guide you? This is the Endress Hauser applicator. An important thing is what you will always find is that you shall not exceed 0.3 Mach. Mach number is very important. So that's 30% of the speed of sound of the gas. So for hydrogen, the speed of sound is relatively high, 1,000 meters per second. So you could go up to 300 meters per second or something like that. And these limitations are implemented into applicator. It depends on the gas, and their applicator is a real good engineering tool.
Yeah, and applicator you can find easily just visiting endress.com/applicator is the most quickest way. And Oliver, that's all the questions we get now already. Thank you in the chat for the answers. And with that, I would like to say thank you, Oliver, very much for giving us these insights, and thank to the audience for listening to us, and have a good day.
Okay.
Bye.
Perfect. Thank you. Bye now.